we're going to be looking at the rest of 4 Charlie. Looking at the transmit path, the receive path, standby loopback path, and order wire. And pretty much this is it for the day. We'll go over 5 alpha. It's very brief. So let's take a look at our transmit path. Now I put this in here just to get you guys reminded that this is what a circulator does. You'll see that passive non-reciprocal. The idea here is it can, just because of the makeup of its impedance, can determine what's the receive path, what's the transmit path, and which one goes out of each. One can go in, the other can't go out. So this is my theory on just this device right here. Ports 3 and 1 are input-output areas. Port 2 is where the antenna is, and it's both transmit and receive. So it's a duplex, full duplex on that part, but 1 and 3 are just simplex at that point. We look at duplexers. I think I'm pretty sure I showed you this one earlier. And this is another idea of what a diplexer is. So when we look at the baseband path, and I told you beforehand, you got to have your C's and D's out if you have them. They are electronic, and that's what we're going to be going through. If not, follow through the tech order on the transmit path. You can see the TOs right in front of us. Paragraph 5.2.2.1 all the way through 3. And we're going to start on the baseband assembly, which I think is page 4, and work our way through it to page 5. Again, you'll see that we start with transmit path, because sometimes the transmit path is the best path to go through, because the receive path normally uses everything that not everything, but portions of the transmit devices in order to formulate some receive here. So with this particular thing, you will notice, and I'm going to move this real quick. You can see that we are on page 4. We are starting at the bottom right-hand side where it says transmit mission traffic. So the idea here is on the back of the baseband assembly, there's a Canon plug or there's 2 BNC cables. The BNC cables are fiber optic, and the Canon plug is for, I think it's CDI. We're going off the back of the baseband assembly into it, and the first place we're going to go to is the attenuator. Now you'll see that this is on the front panel of our baseband assembly, and let me go up one, blow this up for you. And you will see the transmitter XMTR at the bottom. You go all the way up and you'll see 2 knobs. This is your attenuator that you're looking at on page 4. You'll see that the top one goes from 0 to 20 and the bottom one goes from 0 to 10. It says on that little breakout that I showed you earlier, it says a 0 to 30 dB attenuator. Well, the way that works is you put the top knob on 20 and the bottom knob all the way to 10 and you get 30. So if you wanted to get something like, oh, I'm going to pull something out of my hat here, 15, you would have to go to the top knob here, turn it to 10, come down to the bottom knob here and turn it to 5 to give us 15. So we come into the attenuator and you can see that normally multiplexers, depending on the length of their cable, and digital information has a tendency to lose its strength the further that cable is. We want it at 3 volts peak to peak. It has been my experience when we put the FCC 100 connected up to the the back of the baseband assembly, we would literally have to use that. Why? Because it's like a 10-foot cable. Now, if you had like a 30-foot or a 50-foot, it's probably going to be a little bit different. But we normally were in the 15 to 25 dB of attenuation when we use the SCC 100. This is to get us that constant aggregate in strength to come into our system so we don't oversaturate it. We go into something called a baseband filter. Now, what this baseband filter does is it lets that aggregate go through, but it's going to what I call clean off the signal at the upper end at 8.5 megahertz. At 8.5 megahertz, there's a reason why, and the idea is to literally block anything on there, and that's the cleaning off of it. So we clean the noise, anything that's been generated on it. Is there a possibility something else could be on there? Of course, there's always something on there, but just like with anything else, we're getting ready to put on an 8.5 megahertz signal at a later time frame. So this is where we clean it up and we send it to the summing buffer amplifier. Now, if you hadn't noticed, we're following the bold lines for our signal path. Now, this summing buffer amplifier, if you thought back to Dolan Hall, anybody remember, I think it's called a common base transistor? No? Maybe? Anybody? Yes or no?
Yes, sir. Common base. It was two transistors stuck together to form essentially an amplifier, wasn't it?
No, I think you're looking at, oh geez, it's called, I can see what, yeah, well, you got common base, you got common emitter, common collector. Well, in this scenario, common base is used for combining a couple signals together to give us a unity of one. What does that mean? Well, it's taking two signals, and instead of one being stronger than the other or amplifying, the idea is whatever that strength of that signal is, whichever one is the stronger or the weaker, they're going to make sure both of them are equal, so when it comes out, that's that unity of one. So that's what a common base does. All right, we'll wait on Mitchell here real quick. So you can see that we're going to combine our aggregate, which is our CDI and pseudo NRZ, with something called order wire. Order wire is that auxiliary channel that we talked about earlier yesterday, I think, and just gave you an idea that it is that channel we're getting ready to put on it. We'll come back to it when we cover order wire. So you can see the 72 to 4608 kbps, that's CDI. The 6144 kbps is the pseudo NRZ. The 8.5 is our auxiliary channel that we call order wire. That order wire helps us troubleshoot the equipment or gets it up and running. Mitchell, you back? Not. So while we're waiting on Mitchell for a brief second, Rodriguez, question for you. How do you compensate for quantization errors?
Excuse me, sir, say again.
How do you compensate or correct for most of your quantization errors in the PCM area when you're converting analog to digital? You can say I don't have one.
I would like to say filtering, but I'm not 100% sure with that.
No. Raina, any idea? You can say no. So Mitchell, while you were in the bathroom, I asked the question, how do you compensate for the quantization errors in step 2 of the PCM? Salem, do you have an idea? Schaefer?
Isn't that what the input attenuator does?
Negative. Jay?
Uh, uh, sorry, can you repeat the question one more time? And then I think I.
Okay, yeah, your mic is cutting out. I wonder if you're having problems hearing on my end, on your end. The question
Yeah,
is,
can you.
yeah, on
Go ahead, sir.
PCM, we have quantization errors on the second step. What do we use in order to compensate for them?
Non-uniform quantization.
Yeah, bingo. That's it. Non-uniform quantizing. Looks like some studying this weekend. All right, so we left off with the summing buffer amplifier. Now we come out of it with a combination of our order wire and our aggregate, whether it's CDI or pseudo NRZ. We're going to go through something called a diplexer. And this diplexer is a passive device built of filters, capacitors, and inductors is basically what it is. Now it's going to let my order wire and baseband signal go out to the back of the baseband assembly to get to the RF assembly. It's going to block the 70 megahertz from getting on our baseband and order wire line, so it doesn't feed back into it. It's also going to filter out our baseband and order wire from getting onto the 70 megahertz line, which is above it. See where the 70 megahertz is on that red square, right above it. So we're going to go out the back of the baseband onto the 2-foot cable and come into the RF assembly. Again, we're following the bold lines. Let's take a look at the first place we hit. Again, it's another diplexer. This is meant to filter anything that goes onto our baseband and order wire line. In other words, the 70 megahertz is not going to get on it. Now, 70 megahertz is a receive signal. We want transmit on this path. So we're going to carry it over to something called a amplifier. In this scenario for our C's and D's, anything that you see in a triangle like this is normally an amplifier. This particular device, because either you have a 2-foot or a 150-foot, it is actually called a compression amplifier. This compression amplifier does two things. First of all, it amplifies all the time. However, if you have the 2-foot cable, more than likely you're going to have some compression with it, because there's a threshold of amplification that it's going to do to compensate for just for the 2-foot cable, but it's really going to amplify if you got the 150-foot cable. So with the 2-foot, probably a little bit of compression. With the 150-foot, it's going to amplify like crazy unless something weird happens. So we're going to amplify our signal. But we're going to go back to that BCD. Remember those thumb wheels on the front panel of our RF assembly? Well, they call them a transmitter encoder. This transmitter encoder is what you're going to put into the RF assembly for the frequencies that we need to do. That transmitter encoder is actually a BCD device, so whatever number you got onto it, it determines the ones and zeros that it's going to send through the data switch over to our phase lock loop system and tell the VCO over here what to do. So the data switch is the key because we are in operate mode. Everybody remember that switch I talked about on the baseband assembly saying you have standby or operate? Well, operate means that you're transmitting out. Standby means that you're in a loop back but nothing's coming out of the antenna so you can safely work on the equipment. We're going to run that through over to our VCO to tell it what to do. Now, this part, you will see that this is part of our basic radio. Remember how basic radio works? You have the first step is modulation. Second step is up conversion. You're going to take that up conversion, you're going to amplify it, and you're going to send it to the distant end. That's in a nutshell. So 3 steps. The objective is to transmit baseband to the distant end. This is your first step, modulation. So we're going to take that VCO, and it is basically a discriminator because it's in FM, frequency modulation. Now with this, when we up convert it or modulate it, we're going to take it from baseband to IF. This particular IF is between 7.2 to 7.625 gigahertz. So BCDs tell the PLL what to send the VCO what to do. Our next step of this sending baseband to the or transmitting baseband to the distant end is the up converter. So let's take a look at the up converter and what it has. Now, you heard me tell you about the 7.2 to 7.625. Well, if you take times 2 both those numbers, you'll actually get the frequency range of 14.4 to 15.25. Realistically, that multiplier is actually an amplifier. How does that work? Well, the confines of basic information on what an amplifier does is it's going to amplify the 7.2 to the 7.625 gigahertz and amplify it like crazy. What happens with FM generates a boatload of harmonics. Anybody know what harmonics are in the wonderful world of RF?
Yes, sir.
What is it? I hear it.
They're the frequencies generated that are nearby, above or below your carrier signal, and FM.
Okay.
Which they're created by the effects of modulation, or not modulation, heterodyning.
I disagree with you on there because modulation is one technique. Okay, modulation is different than heterodyning.
Yes, sir.
With modulation, you normally get an upper and lower sideband, but your audio, because it's so low, and the impedance of the circuit blocks the audio frequency because it wants to let the higher frequencies go through. That's the reason why when it appears that it's heterodyning, which is in some cases true, but we call it modulation because of that one little factor, because heterodyne, the definition would be when you take a nonlinear device and you combine 2 signals, you're going to get 4 out. Well, in this case with modulation, you only get 3 out because the impedance of the circuit wants the higher RF, not the lower RF, so it gets trashed. It's not unable to get through. I've been able to look at that when we do single sideband. They have a balanced modulator where you can actually see the upper and lower sideband with the carrier, but it's the impedance of the carrier that gets taken out by varying that impedance. And you can't even see the audio because we've looked down in that area with the audio and there is the impedance of the circuit just weeds it out. So hopefully that. But you are correct in saying when you take and amplify it, you're going to generate harmonics. Harmonics being a multiple of the frequency. With this in mind, your first harmonic is going to be between whatever you dialed in, which is a 7.2 to 7.625. The second harmonic is actually going to be the 14.4 and the 15.25, and then the third harmonic, the fourth harmonic, and the fifth harmonic. Normally in the radio world, anything below the first order harmonic is called intermodulation distortion, and they don't even pay attention to it. Now they do look at the upper and lower sidebands, but what is the stuff that's below it, normally it's noisy in that case. Now most of our earlier radios worked just like this, in where we would produce a second or a fourth harmonic and take that fourth harmonic and use it as an operating frequency. In this case, we're going to use the second harmonic, but we still have a problem, don't we? We still have all the other harmonics. We're going to run it through a bandpass filter and clean it up. What does that mean? Well, we're going to eliminate the first harmonic, and everything from the third harmonic and above, we're going to eliminate. That's what that bandpass filter is going to do. When we look at our second part of this story, you had, not second, it's actually a third part of our basic radio. So you've had modulation, went from baseband to IF, IF to RF, which is past the multiplier, and now you're going to have a high-powered amplifier, which is going to get us the final output in wattage. This field effect transistor is pretty beefy, so it's going to amplify it up to that 316 milliwatts or 25 dBm. And now we're running into the transmit branch assembly. The first thing we go in through is the isolator. The isolator's job is to keep anything from coming back into our RF section. So once we've produced it, we don't want anything to come back at us. The next part is the harmonic filter. And anytime that you amplify, you're going to generate harmonics, especially in FM. So with FM, because we've amplified it, we're going to generate those harmonics. We're going to take it out with a harmonica filter. Get it? Harmonica? Bad. Next up, we have a transmit filter circulator. Again, this is a three-way. You'll notice it's tied to a pre-selector filter. It has an input on one side and basically an input, or excuse me, two outputs. Well, this one's going to take the way of the least resistance. If you go up, it's through a pre-selector filter. It hits an attenuator. But there's a problem when you go all the way to the top. The switch is not in the down position, so it stays right there. So the only path it can take is this bold path. It goes through standby relay 2. This is in the operate position. So the operate position gives that switch an indication I need to flip in the down position so I can let the RF go through. This is also controlled on the front panel of our baseband assembly. We're going to come up into another circulator, which this one is always active in all three ports. Remember I said earlier that one's going to be an output, the other one's going to be an input, but there is one that's going to have both. In our case, it's going to let the transmit go through and go out the antenna. And that is basically, in a nutshell, everything in the transmit path. That is also quoting things right out of the tech order. Everything that you've seen in the pop-ups are from the tech order. I'm just giving you a little bit more information to get you to understand what's actually happening in the circuitry. I guess that's a disadvantage to you guys because we used to teach down to component level back in the day. Not anymore. In fact, when I looked at the basic electronics in our little area, we got a couple guys that are training one of our staff sergeants in basic electronics, and they're taking it down pretty low. In fact, we used to be able to put a circuit together, and it was called a pinger detector. What that was is, I think it was a monostable multi-vibrator, and had 2 LEDs on it, and it would, when you applied a 9-volt battery, it would alternate between blinking. Pretty cool. You put it together and had a little fun with it. And you were able to practice soldering and cutting your cables and everything. It's pretty cool. Next up, we're going to do the receive path. So we're going to change it from receiving the antenna, go through the circulator. Oh, gee, look, it's another branch assembly, or part of a branch assembly. Again, these are all passive devices, nothing tied to power whatsoever. So we're going to go through our circulator. The circulator is going to be able, because of the impedance in determining what frequency goes where, is going to let our receive go through and block our transmit from getting on that line. We're going to go through this standby operate relay. This standby operate relay is controlled by that front panel standby operate switch. This is in the operate position. We're going to go through that pre-selector. Now on the front panel of our RF assembly, you remember that little dial, and this is the big key, is most of you, okay, Mina, I see it. That front panel is pretty important when you put your frequencies in. So I'm going to go up while he is in the restroom here. Click on this one. Right here, left-hand side where that knob is, you'll see receiver frequency. When people put in their receive frequency on the thumb wheels, they forget about putting the frequency on the dial here. When they talk about a tape, they're talking about a very old style way of changing frequencies, where some of our systems, and you can go online to take a look at them, some of the older stereo systems had a dial that went from, you know, your FM from 88 all the way to 109. Well, on it was a tape. And you could take what's called a cat's eye and move your little dial up and down. Well, this one rotates with a circle. So they taped it on the circle, and when you turn the dial, it rotates left and right. And it's a pre-selector. Pre-selector. Anybody got any questions while he's gone to the restroom? Overwhelming?
Yes, sir.
Remember now, I'm online.
Yes, sir. There's going to be a lot of studying this weekend.
Well, that's fine by me. You know, challenge me. I don't have a problem with that. In fact, I love it. The only thing I got to complain about is if you're challenging me in the middle of one of my games, you know, i.e. World of Tanks, it may take some time to get to you.
Don't worry, sir. I won't bother your gaming time. I know how valuable that is.
Oh, crap. You would not believe how many times I finish the game, and then I'll come to you. Okay? And finishing normally lasts maximum of 15 minutes in a game. So if you put, you know, you message me and I don't see it pop up before I enter the game, yeah, I'm going to play the game. Normally we're out between 10 minutes if it's a good game. On occasion, I've been in games where it lasts all 15 minutes. Normally those are the really exciting ones, built on strategy. And of course, it helps to have Muppets every now and then. Boost your stats. All right. Mitchell's writing. This should be classic. Yeah, yesterday I started it, but I didn't finish it. I need to get it up on YouTube. It'll probably be today on both sessions, and hopefully I'll get these sessions up there available for you too. I got sidetracked with some other work. Normally it takes about 10-15 minutes to do the editing, because I like to cut off the up front and at the end when we're talking and not pertaining to the information, which, you know, that takes the least amount of time, but it's the when you produce it, it takes time. Depending, for example, that hour and a half, close to 2 hour session we did the first time around, yeah, that was a very long session and took a very long time to upload it. And also YouTube on occasion will give me grief. Mina, are you back? Well, that's good, because you can review those. And I keep telling people that most of the people that do the review will watch it again and pick up on some stuff you missed. Because, you know, I'm like you guys. You know, if I'm trying to look at it on a cell phone, it's really difficult. But on occasion, you know, you're able to download it from, you know, the YouTube on your computer and watch it. It helps with a bigger screen. Mina, you back yet? Ah, good. Thank you. I appreciate you guys letting me know in the chat, because, you know, this is pretty overwhelming, you know, like I just asked. Going over it a couple times, maybe looking at the TO while you're listening to this might help too. So we left off with the isolator. Isolator, we've already explained in the transmit side. The idea to keep this one is we only want RF to go through. We don't want anything coming out of that low noise converter coming back through. So the first place we look at, remember, we're going to recover the baseband. That is the basic radio. You're going to have amplification. So we've cleaned it up, and now we're going to amplify it. This is going to take that signal and hopefully boost it enough to where I can put it into what's called the image reject mixer and be able to use that signal. It'll be at the same level as what our VCO is putting out. This next part is a down converter. Now, this down converter, the reason why it's so big is it encompasses a couple pieces to get us that 70 megahertz out. Well, in this case, the image reject mixer, your information from the VCO, okay, is from the receiver encoder. Now, the difference between the receiver encoder and the transmit encoder should be a minimum of 200 megahertz apart. So your transmit frequency versus your receive frequency is going to be different. Now, that receiver encoder is going to produce a signal that is somewhere around the plus 70 megahertz or below the 70 megahertz from the operating frequency. And I'm just going to give you a wild figure here. So if you had 15 megahertz dialed in on your receiver, the pre-selection is going to let the 15 gigahertz come through and arrive at the IRM there. The encoder is going to tell the frequency, or the VCO, voltage controlled oscillator, what to produce, and it's going to be 70 megahertz. In this case, I'm going to do above, so it's going to be 15.07 gigahertz. So when you look at this image reject mixer, The word heterodyne comes into play because it is a receive function. Modulation is transmit, heterodyning is receive. With heterodyning, the actual saying should be with 2 input frequencies, you should get 4 out, which should be the 2 originals. You're going to have the upper sideband and a lower sideband. Summing the difference. Well, in our case, let's just take 15 megahertz or 15 gigahertz. We have the 15.07 coming in. So when I mix them, I'm going to have 15 gigahertz, 15.07 gigahertz. I'm going to have 30.07 gigahertz, and I'm going to have the difference, which is 70 megahertz. Now, all 4 signals are coming out of there. Anytime that we manipulate the signal like this, we always lose a lot of power. So we're going to have some amplification. We're going to run through another amplifier and gradually build it up. And the idea behind that is not to create as much noise before we break it down. This is where the final stages of, I can say we now have the 70 megahertz on its own. So where is the 70 megahertz actually developed is back here in that RARM. That's where it's developed, but it doesn't get cleaned out till here, which is the bandpass filter. If you read what the bandpass filter does, it says, I am centered on 70 megahertz plus or minus 10 megahertz. Now, what does that mean for a bandwidth? Because that's what it is, a bandpass filter. It means that from 60 megahertz to 80 megahertz is what I'm going to let it go through. And again, we've manipulated the signal. We cleaned it up. It is now 70 megahertz, and that's it. It's coming out of there. We're going to amplify it. We're going to amplify it for our AGC and give us an idea of what that received signal level is. We're going to run it through a Diplexer. Again, it's going to keep the 70 megahertz from getting down on the transmit line, but it's going to let it go out the back of the baseband line. We're going to prevent the baseband from getting on our receive line. I know it's a lot of information on that. Picture the Diplexers, okay? One on the RF assembly, one on the baseband assembly. You got an input and output as well as an output input on one device. So one side you have baseband and 70 megahertz, the other side you have both. And the idea is to keep them separate when they come in and when they go out, if that makes sense. I like to call it a two-way highway on that 2-foot or 150-foot cable, because that's what it is. You got the 70 megahertz going this way and the baseband assembly going on that side, or baseband on that way. So you have 70 megahertz, you have the aggregate, all on the same line. One's going one way, one's going the other way. But when it enter or exit, the idea is to keep them separate when they're in the baseband assembly and when they're in the RF assembly. So when we connect this up to the baseband assembly, we are going to come in, go through a Diplexer again. That's the whole idea behind it. Is in this case, I'm going to block the aggregate from coming in on my 70 megahertz line and let the 70 megahertz go through. And of course, first thing you're going to hit is an amplifier. Why? Well, 2 foot's not a big problem. It's the 150 foot is a problem, because you're running all this DC and aggregate signal down the line. You're probably going to have some loss. So the idea here is I'm going to get us enough amplification to make it to where I can determine what to do with it. You'll see that we have an IF demodulator. This is the basic portion of, let me redo this. This is where the demodulation happens, and we go through a process. So when you look at the IF demodulator, it's going to take the IF and convert it to our aggregate signal. So we cleaned up the 70 megahertz, and now we have the signal that we want. Well, sort of. And the reason why this is all encompassing is because we only want the mission traffic in our case. We don't want the order wire. So that's the reason why I included a couple other devices for this. The demodulation happens in the IF demodulator. You're going to amplify it and run it through a low-pass filter. Now, the idea behind a low-pass filter, and remember now, you got 8.5 megahertz running through this. That is our auxiliary channel, and you really don't want that on with the mission traffic. Now with the low pass filter, because we amplified it, we're going to have to block some of those harmonics. We're also going to have to start weeding off the 8.5 megahertz. So basically we're cleaning it up, and then when we get to the subcarrier notch, this is where we block the 8.5 megahertz order wire signal, and we have a clean baseband signal. Okay, so that's the reason why we got to do all that other stuff in there. This is only going to pass either CDI or NRZ, pseudo NRZ. On the front panel, you're going to have something called FO and GM, FO being fiber optic and GM being group modem. Where can you find it? Well, let's go back and look at this bad boy. If you take a look on the receiver baseband unit, go all the way to the top, you will see GM and FO. You're going to keep that in whatever position you need it in. If you're running fiber optics, you need to be in the FO selection. If you're running CDI, you're probably going to be running GM. Next up, we have an attenuator. This one's a little bit different. This one only goes from 0 to 10. Where's that? Right below the GM switch. Because we don't have such a strong signal, there's probably going to be very little attenuation. Now, how do you figure out how to get it to where it's supposed to be? See this meter on the left-hand side? You're going to swap this over to the receiver baseband, put that selection switch in there, and then you'll be able to determine what it is that you need to attenuate. If it's below the green, then you probably have to switch it closer to 0. If it's above the green, you're probably going to have to switch it closer to 10. So that's the selection switch. Same for the transmit baseband. If it's really strong, you got to use the meter. It's got to be in that transmitter baseband selection right here on the left-hand side, and then you adjust its attenuator to where it is in the green. Now, I can tell you, when you are doing your setups, we have no multiplexer. So when you get to that stage where it says adjust the attenuator, it's assuming that you're putting a multiplexer in there. I have not seen any outside of the green, but it's kind of like a default to it. So unless you put a multiplexer in there, you're really not going to be able to adjust for it. Are there any questions on the receive side of the house? No? All right. Let's go with the order wire. Order wire is pretty simple. You can see that the order wire is very basic. Can everybody see my mouse with this one? It's really hard. I can't get the mouse to blow up when I need it to. Normally, when I have that mouse selection, I don't know what it is about when I click Discord and click into OBS, it goes back to its very small size. So In the middle of this particular C and D, it is your baseband assembly. It's on the C's and D's. I'm going to point you to the right-hand side of the C's and D's. You will see that there is a speaker about in the middle, below the mission or receive mission traffic. Above it is a connector. That connector goes to a handset, not a headset, handset. Has an input and output, goes through your order wire intercom. You'll notice that the bold lines, you can see the arrows when you get down to the transmitter subcarrier generator. Does everybody see that? Anybody not see it? I think probably behoove me to do some animation with this just to give you guys a better clue. All right, with this transmitter subcarrier generator, you're taking your voice and converting it, when you're transmitting, converting it into a FM signal at 8.5 megahertz. There's a discriminator in here, so you have modulation to FM. FM goes to your summing buffer amplifier, which is the next stage, and it's going to combine your order wire, which is your voice, and it's going to convert it with, or combine it with, the baseband signal of either CDI or NRZ. Because if you take a look at this logically, the 8.5 megahertz should not interfere with your baseband, because I think the max on your baseband is 6.144 megabits per second. Well, the 6.144 is not high enough to create problems for the 8.5 megahertz. So theoretically, you have an FM signal and a digital signal being modulated in the RF assembly. Now, when you come out of the RF assembly, for example, if the distant end is talking to you, you're going to hear it, and the way you're going to hear it is, remember this IF demodulator up here, top left-hand side next to the cable AGC? You look at the bold line, and it's going to come down, and it will not use the aggregate. It will only demodulate the FM carrier. It looks at that aggregate and goes, what do you want me to do? Okay, it basically blocks it there. So when it comes down this line, this is what you're going to hear on your handset. So the handset does two things. Handset, you're going to talk into it to talk to the distant end, or you're going to talk, or they're going to talk to you, and you're going to be able to hear it. Now, there's a couple things that need to be in place. First of all, when you're using order wire and you need to talk to the distant end, go back up here, and whoops. Let me blow this up for you. Be bigger. All right, left-hand side, where the meter is. You're going to go up where you see a summary alarm on the right portion of the standby operate switch. If you are in standby, above the test tone switch is two switches. One is a call, the other one is intercom and order wire, where it says INT and OW. It's below the speaker. If you are in standby, the INT and OW should work. When I say should work is, you can talk between the baseband assembly and the RF assembly. The RF assembly is going to have a headset. So you're going to be able to talk to each other. And the reason why you want to talk to each other is if you're setting up and you're 150 foot away, it's really difficult to yell at each other. So by using the headset and handset, you can talk to each other. Now, what happens if you want to talk to the distant end? Well, let me explain the dial right below the speaker there, that INT and OW switch. If you are in INT, that means you're talking between the RF assembly and the baseband assembly, no one else. To talk to the distant end, the switch has to be in the OW position, and your standby operate switch needs to be in the operate position. You do not know how many times I've had to go, oh, it's not working, it's not working. I come over and I find out that they still have it in intercom, but they got it in operate. Well, intercom means you're only going to talk between you two, the RF assembly and the baseband, not to the distant end. It's when you put it in order wire, because order wire means that you have that auxiliary channel to talk to the distant end. Order wire in operate means you should be able to talk to them unless there is a frequency issue or a dish pointing issue. So that's how that works for order wire. Order wire is used for two purposes: intercom between the RF assembly and baseband, or order wire where you can still talk between each other, but you can talk to the distant end. So let's take a look at some of our information that we have for you. Okay, and you can see that it routes the signal to the transmitter baseband LRU, intercom order wire switch, in the order wire position to talk to the distant end. Transmitter subcarrier generator, again, that's where you're going to modulate and get that signal out to the distant end. There's also something called test tone oscillator. Okay, safety tip. If you have the headset on, don't put it on until you're ready to talk to the distant end. If you have this on, if you have your headset on, and you switch it into test tone, be prepared to yank those headset off real quick. There is no volume control for the headset. There is no control for the handset. The only control is for the volume control for the speaker. That is it. I don't know why they didn't do that. I can only imagine that because of the attenuation that is there for everything is the reason why you're able to hear everything in a decent volume. That's just my opinion. I'm not allowed to pull the actual schematics out and take a look at it. So there you have your order wire. Again, there's a test tone detector. You'll see the lights on your baseband and RF assembly will illuminate. They actually have T/T on them. In fact, let me go back to this one and give you an idea where they are. You can see, here's your transmitter. Down at the bottom of your LRU, you will see T/T, and there's the white light for your test tone. How do you get test tone? Well, in the baseband or order wire LRU, right here it is. Baseband, you see off, and then you'll see order wire. Well, you're going to check both of those in transmit and receive. So you actually look at the receive LRU when you're in loop back, which is standby. You guys will see it on Monday. Okay, standby loop back. Here's the key to standby loop back. You'll notice that we are on the transmit. I shouldn't say transmit. It should be your standby loop back form, but it is the RF assembly. Now with the RF assembly, excuse me, you'll notice that we have a lot of bold lines in there. The easiest way to explain this is the standby loopback switch means that you are in standby. What does that mean? Well, let's go back here to our front panel. See our standby operate switch on our OW LRU next to the summary alarm? This switch is in the standby position. And standby means you're in loopback. Overall, the big thing is this standby switch right here between the receiver encoder and transmit encoder goes to the data switch. Well, why in the world would we have that controlling the data switch? Well, remember we told you about frequency diversity, and our transmit frequency has to be 200 megahertz above or below the receive frequency? Well, if you put the transmitter encoder in line and you're doing a loop back, you're not going to receive it. So what they came up with, the engineers, said, hey, if I flip this in standby, I'm going to use the receiver encoder. I'm going to use the data switch to change what encoder I need to go for. So with it in operate, it's going to use the transmitter encoder and let the transmit signal go out. But in standby, the switch is going to take the data switch and say, hey, use the receiver encoder. Now we have the receive frequency coming in on the same line as, well, our transmit frequency is going to be the same frequency as our receive frequency now. So now we can do a standby loopback. And of course, we're going to put order wire on there. We're going to put a test tone on there just to make sure things work properly. You still have modulation in there. Why? Because if you see the bold line is coming through the Diplexer, there you go. So either way, you're going to have that loop back and be able to check everything out. Now, if you take a look at the Microwave LRU, well, what the heck is a Microwave LRU? Well, see the Microwave LRU? Just like you have the synthesizer LRU. Hey, this is not a bad idea. You have the control and distribution LRU. There's your RF assembly I/O, input output. So you can see, just follow the dotted lines, and those are parts of your LRU. So again, data switch comes through, tells the VCO, the phase lock loop, what to do. You also have your baseband assembly with your order wire coming through. You have a test tone detector, phase lock loop detector, all within this box. And for those of you trying to figure out what phase lock loop is, well, when the data switch tells the phase lock loop what to do, it's going to send a voltage down this line up to the VCO. That voltage is going to tell the VCO what frequency that you need to be on. Well, you'll notice that the portion of it goes up to a divider and then comes over to another divider. And what it's doing is it's generating a square wave frequency of, or representation of, the VCO. When it gets to the phase lock loop, the phase lock loop is going to compare it to the encoder and what it's supposed to be using. And it's going to either send a voltage, it's going to increase the VCO to get it on frequency, or it's going to decrease the VCO on frequency. Now remember, these are happening in milliseconds. And that right there tells you the frequency accuracy of the oscillator. Remember we talked about that term earlier? So hopefully you get an idea of where the LRUs are, how standby loopback is working, as well as what looks to be like a transmitter synthesizer, your LRU for synthesizer, control distribution LRUs. Those are the LRUs. And is there any question on standby loopback? I'm so confused. Yeah. And here's the information on standby loopback. Data switch is the key. You put it in standby mode, you're going to have loopback. What does it control? The relays. Well, that's what I wanted to show you. Get my arrow back. Oops. All right. Where does the loopback happen? Well, you notice that when we took our RF frequency, we came through this switch. Well, with loopback, this switch toggles in the up position. You've got a dummy load here, not to be confused with your neighbor. This transmit filter circulator is going to send the signal up to this pre-selector filter because it's dual, up through the attenuator, and it's flipped this switch in the down position. It goes through the whole receiver section. None of it goes out the antenna. None of it. So that's how the signal is being able to get back around for loopback. So we've gone through purpose, operating characteristics, types of traffic, equipment, and signal flow. Mainly signal flow. Any questions? Again, please contact me. I can do a call or whatever you need to do, and we can walk this thing through. Again, do whatever you need to do. If you guys need some more help on the weekend, you know, I'm open. Just give me a time frame. All right, we got one more to do, and we are done. We got Unit 5. This one has identify basic facts and state general principles of controls and indicators. I think we've covered this in great detail going through Chapter 4. Right there. And I've shown you on the front panels of each, trying to get you guys to see what is going on. Page 4-2 through 4-3 gives us the RF assembly for table 4-1. For the baseband assembly, it's pages 4-4 and 4-6. Now, I think it was yesterday, I took you through the tech order and showing you those pages. So if you want to know what those indicators mean or what their functions are, there you go. I highly recommend that you scan through that. You don't have to memorize it. You just have to look through it. Just a suggestion. Any questions? No questions?
Yes, sir.
Everybody's ready to go, oh no. All right, so here's what we got. Today at 1 o'clock, we have homework due. So you should be able to finish up the rest of it using the signal flow. Hopefully you were keeping up all through the time, and all you got is maybe, 10, 12 questions left, and you're going to have to use a tech order for that. Again, the tech order is available for the test. Do not try to rely on your memory. Verify those answers on the test. Very important. Is there any other questions? I noticed somebody was writing. Okay. If there are no more questions, we'll see you at 1 o'clock then. You guys have a wonderful lunch.